Good morning, girls. In this PPT, we are going to see the basics of nanotechnology, nanomaterials as part of first unit, and as well as elaborated information of nanomaterials, their applications, their properties. All this also deals in this PPT. In the second unit, you'll be having carbon nanotube separate topic that is represented in unit 2 PPT differently. So this unit is taken for both unit 1 and 2 together, except carbon nanotubes. So the contents, if you see in this PPT, are like introduction about nanomaterials, then the material types of materials and making of types of materials, features of nanostructures, application of nanomaterials, and technologies with which they will be developed, and nano-dimensional materials, zero dimension, one dimension, and two dimension structures, examples, their size effect and fraction of surface atoms, then specific surface energy, surface stress, and effect on the lattice parameters. Then it is continued to density of states, then synthesis procedures like bottom up and top to bottom approaches. Then precipitative, reactive, they like synthesis processes for making the nanomaterial. Then scaling while preparing the nanomaterials and their potential use, everything are seen in this first PPT. So when it comes to nanotechnologies, basically the materials are very precise, and with respect to size, everybody knows that nano in the sense very small. So application with compact size, not only compact size, is also application with respect to low power or device parameters, and the dissipation current or everything will be very of nano scale. And so the subatomic molecule level, the material will be made. So nanometer scale will be considered even atomic subatomic level. So to produce a nanomaterial, we require a fine type of material, fine quality or fine quantity of material, and the characteristic properties of such fine quantity is very essential to capture. So why nanoscale? Why not other? If you observe that nano in the sense, everybody aware of that, 1,000 of millionth of a meter. So basically, compact nature is interesting of every people, applications, devices, or anything. So materials of nano are different comparatively larger scale materials. So as the technology is growing, nano size have taken lead, taken importance. So every material, every device is made up of nanomaterial. Gradually, nanomaterials have taken importance. And this is the scale. If you observe that from 10 to the power of 6 nanometers going towards left hand side, 10 to the power of 5, 4, then 3. So 10 nanometer, when it comes to 10 to the power of 0, 1 nanometer. So down to the scale, it is written in terms of from the nanometer, micrometer level, nanometer, reaching to nanometer towards left hand side. And the examples for at each every nanometer, see, for example, at 10 to the power of 0, 1 nanometer, the DNA diameter is of that size, and protein is of size of 10 to the power of 1 nanometer, that is 10 nanometer. Similarly, 150 micrometer human hair is of diameter 150 micrometer. Similarly, the grain of sand, if you observe the sand, a small particle of sand is of 1 mm. And similarly, within the human blood cells, red blood cell size is of 10 micron meter. And transistor, the one which will be used in the ICs and all, is of size 35 nanometer length. Similarly, above which carbon nanotube diameters, that is 5 to 10 nanometer. It is one kind of polymer and have got many applications. Nowadays, people are using in preparation for the batteries and semiconductor materials alternative to the mass transistors, where size reduction is important, right? So similarly, atom, if you see the very least sized atom, 0.1 nanometer. So like that, as you go down to the size of the particle is getting reduced, and it is essential to understand how important a nanomaterial. So nanotechnology basically defined in such a way that a molecular or macromolecular level in the length scale, approximately 1 to 100 nanometer range. And similarly, at the system level, when you use nanotechnology based device for making the system, so the properties and functionalities are a bit different compared to larger scale. And generally, when you go for nanomaterial, the system which is made with nanomaterial, from the scratch, from the atomic level, one should take care of the device characteristics. So this is broadly brought to you to see that nanoscale contaminants, generally that we see, we regularly encounter in daily life. And see, these red markings are horizontally represented, which are types of filtration. So, and the upper arrow down were shown, which are nothing but the types of particles which are that size of nano size. And then so filtration methods, if you see, one is conventional method, and then using this conventional method, pollens are like the flower, outer parts of the flower, the tiny central particles of pollens, a small dust particle like that. So those of a size of 10 to 100 micron meter can be done using conventional filtration. When it comes to aerosols, it requires, because the size of the aerosols is 1 micron meter, so it requires a particular method of filtration, that is microfiltration. Similarly, when it goes down to another technology level, 10 nanometer to 100 nanometer, so their filtration is ultrafiltration is required. Similarly, when it comes down to still tiny particles, zero point 0.1 nanometer to 1 nanometer, the filtration is reverse osmosis method is required. And when it comes to conventional, now which are to do the filtration of pollens are there. As an example, protozoa, which is of greater than 2 micron meter size available, and microbial cells which are greater than or equal to 1 micron meter, using required filtration of microfiltration. Similarly, viruses, generally for any disease, generally we say this is the reason or virus, that viruses generally are of size 10 to 100 nanometer. So they require ultrafiltration or microfiltration techniques. And similarly, hemoglobin, it is of 7 nanometer. So that is required still less size, no? So it requires filtration of type ultrafiltration. Similarly, H2O particle, that is of size zero point 0.2 nanometer. So it's very, very small, tiny particle compared to all. So it requires reverse osmosis filtration method. So the same thing is continued in the next slide, like filtration techniques, typical pore size or range, then what it removes if I use that kind of filtration technique. Then, so generally where we use the application. So reverse osmosis RO, technique generally needs a filtration with the size range of zero point 0.1 to 1 nanometer, and which removes water molecules, that is contaminated water molecules or dissolved salts, ions, and which is generally used in water purifiers. Then similarly, ultrafiltration UF, that is 1 to 100 nanometer types of particles will be filtered. So there we can see to remove unwanted proteins or viruses. That will be used in the application like sterile filtration or removing macromolecules. And similarly, microfiltration is of the range 100 to 1 micron. That is to use to remove bacteria or some viruses. So in real applications, wastewater management or beverages industry like that. And conventional filtration, that is greater than 1 micron for the particle size. So protozoa, suspended solids are the examples where we can see the removal particles, and this will be used at household filters or air filters are the examples for this technique. Similarly, contaminant size, that is top arrows, just what we have seen in the previous slide. So if we start from smallest particle, that is H2O molecule, that is too little or too small, that cannot be easily go through from the normal filtration. That means that is very hard to identify the filtration of such kind of small molecule H2O. So it generally it passes all because the available filtration methods cannot stop such kind of tiny small. So we need to identify very different filtration methods for that. And then hemoglobin, that will be filtered or using ultrafiltration, is of size 7 nanometer. Then viruses 10 to 100, ultrafiltration or tight microfiltration. Similarly, microbial cells are of size 1 micrometer, that will be used the technique of microfiltration. Then protozoa, that is 2 micrometer, that can be used to filter that using conventional filtration. Then when it comes to so what are the materials of nanotech? So if you see nanostructure and then size, and then what are the examples of materials or application if you see. So clusters or nanocrystal quantum dots are of size of the radius of 1 to 10 nanometer. Then these are seen in examples like insulators, semiconductors, metals, magnetic materials are all these available with this size. Similarly, other nanoparticles are of radius 1 to 100 nanometer. So that will be seen in ceramic oxides or bulky balls. Similarly, nanowires are of 1 to 100 nanometer, can be seen in metal semiconductor oxides and sulfides, nitrides, and nanotubes. So nanowires are different. Nanowires are like a stretchable strands, whereas nanotubes are like curved shape. So these nanotubes are of diameter 1 to 100 nanometer, whereas nanowires are of diameter 1 to 100 nanometer. But the application is different because nanowires are used for metals or semiconductors kind of things, real scenario. But nanotubes will be used for including pollutants or layered one after the other layered materials like that can be used, these nanotubes. Then when it comes to the next slide, wait a minute, girls. So this is one example for nanotube. So though the picture is shown very big picture, but it is very of small, tiny shape. And these are few examples for nanostructures. So noble metal nanocrystal with cyclic pentatwinned twinned structures. So these are different sizes of nanomaterials like 10 nanometer, 100 nanometer. The star structure is 100 nanometer, and this octagon kind of structure is of 200 nanometer. Similarly, the star structure is of 100 nanometer. So these are all having different sizes and having different applications. Then when it comes to next slide, few more examples. So not only 100 nanometer, 200 nanometer, 10 nanometer, but is also available with as a grain, nano grain, like a powder. Okay, so nanomaterials that has unique novel properties. Now we are looking into what sort of properties the nanomaterials are having. So at nanometer scale, what sort of properties generally the materials will have? Let us see. So generally, nanomaterials are formed incorporating structuring of nanoparticles. So generally, nanoparticles are again subdivisions of materials. Subdivision in the sense up to nano sized crystal materials. So these are like the nanocrystal materials or nanopowders or nanotubes, a sequence of nanoscale of C60 atoms arranged in a long, thin cylindrical structures. So nanotubes, the very slide of first example, you might have seen nano tube that is strong mechanically and very pure conductors of the electric current. So applications of the nanotube includes resistors, capacitors, and inductors and diodes. So the nanotube is made with the kind of polymer, and because of the resistive property, it can be stretchable to any layer, such that the application of such layers will be resulting either the behavior of a resistor or a capacitor or inductor according to requirement. Based on the orientation of the nanotube, not only orientation, based on the thickness and thinness, we can get different kind of behavior of the device. And these are few examples of like nanomaterial properties. So catalytic property. So generally we can see the properties under chemical, under mechanical, under what do I say, biological properties, but very few electrical properties and mechanical. All this only few considered in this PPT. So catalytic property, better catalytic, the nanomaterials have a better catalytic efficiency through higher surface to volume ratio. And when it comes to electrical, these nanomaterials have good conductivity in ceramics and magnetic nano composites. And instead of big scale materials, we can use nano that increases electrical resistance in metal. Similarly, under magnetic applications, so the properties like increased magnetic coercivity up to critical gain size and super magnetic behavior. Similarly, when it comes to mechanical field, so the nanomaterials improves hardness and toughness of metals and alloys ductility and super plasticity of ceramic. So not only the easiness of making the nanomaterials for mechanical devices, whereas their outcomes or results are very flexible and will be improved compared to large scale materials. Similarly, optical field, if you see the properties like spectral shift of optical absorption and fluorescent properties, increased quantum efficiency of semiconductor crystals. And spherical, that is another field in which the properties of nanomaterials have selectivity, high selectivity, and halo spheres on specific duct transportation and controlled release. So that is all spherical in medical applications. Similarly, biological field, the properties like increasing permeability through biological barriers. The barriers are like membranes, brain barrier, etc. And is also biocompatibility, one biological material to other. So biocompatibility also can be observed with respect to nanomaterials. Now, when it comes to properties individually into different fields like physical properties. So the physical properties basically concentrate on size, the shape, specific surface area, aspect ratio, and agglomeration, aggregation state, size distribution. So these are all matter when a nanomaterial is made for the application of electrical or mechanical, and basically the structure of the material, and including crystalline and defect structure and solubility. So, and when it comes to chemical, the properties of nanomaterial will be concentrating on structural formula or molecular structure. Structural formula in the sense like what kind of nanomaterial, like silver bromide. So the components, the combination together, what sort of compound to be build the nano compound. So like that, a structural formula is one of the property. Molecular structure, molecular structure in the sense how many atoms with which the nanomaterial is compounding, like that. And composition of nanomaterial, degree of purity and impurity, additives, and phase density. Phase density is like when two materials are combined, they have the different shape. The combination of two atoms may result in third atom with different phase. So phase identity, then surface chemistry, composition, charge, tension, and then reactive sites, physical structure, photocatalytic properties, zeta potential, and then hydrophilicity, lipophilicity. All these are matter when it comes to when nanomaterial is used under chemical field. So generally, some common type of features of nanomaterials are look into, which are like size. Basically, the nanomaterial size will be limited to the nano level of 1 to 100 nanometer. Then it should be chemically active. So, with respect to various applications, like whether it is physical application or chemical application or biological, so the nanomaterial should be active in those particular environment. Then, and it should be active to color change, to identify, for example, like using some material, using some what do I say, to identify cancer cells. So based on the color, based on the size may change, the color may change, nanomaterial color may change. So all these during application, it should be very proactive. Then it should be strong and hard and ductile. So these are general characteristics of a nanomaterial with various applications it should follow. Then depend upon the size of nanomaterial. Uh, Generally, nanomaterials are properties under optical can be represented like light absorption, or scattering the light based on the size of the materials. So if it is the material, nanomaterial is of less than 20 nanometer, the material property is adsorption. Whereas if the nanomaterial is size is of greater than 100 nanometer, then with respect to optical, the nanomaterial behavior is scattering. So based on the size, the behavior is changing if you observe that. Less than 20 nanometer adsorption. If it is greater than 100 nanometer, scattering. So, because why scattering, in the sense the thickness of nanomaterial will be more so that absorption cannot happen. Whereas when it comes to 20 nanometer, because it becomes thin, so the optical light, when it falls onto the thin material, absorption will take place. So that is the difference where you can observe. Similarly, nanomaterials will show color change. At bulk level, they are looks like opaque, but when the tiny nanomaterial, if you observe that, they look like a transparent material. So similar example like copper and silicon, and similar in the case of gold, 50 nanoparticles show green color, That means the size of the particle is very less. During that time, it appears like green. Whereas if the particle size is increased to 100 nanometer, it shows like or looks like orange. And if it is greater than 100 nanometer, generally that is the one which we see generally with our eyes, that is color yellow. So like that, color or application varies with respect to the size of the nanomaterial. Okay. Now coming to the properties of electrical field. So electrical conductivity is one parameter that varies when the size of the particle changed. So in ceramics, for example, ceramic in the sense like it's a brick kind of material, hard material. So in the ceramics, electrical conductivity increases as nanoparticle size decreases. So as the nanoparticle size decreases, that means that thickness is reduced, conductivity increases. That is one typical characteristics we can observe in ceramics. Similarly, in metals. So electrical conductivity decreases as nanoparticle size decreases. So as nanoparticle size decreases, the thickness of the material reduces. So particle size is reduces in the sense the vicinity of atom to atom reduces. So that is what the conductivity reduces. Similarly, electrical properties changes with nanoparticle size, and there are four case maybe like one surface structure, their property of nanomaterial behaves differently, change of electronic structure, quantum transport, and effect of microstructure. So these are four properties in which nanoparticles or nanomaterials have greater impact. Now coming to uh, the other slide, that is mechanical properties, in which we have to concentrate on strength, plasticity, hardness, toughness, ductility, and rigidity. So electrical properties are related to like conductivity, whereas when it comes to mechanical, it's like strength, plasticity, hardness, toughness. So nanomaterial shows excellent mechanical properties. So that is external mechanical properties because of the size, basically their volume, fit into system, then surface, quantum effect of nanoparticles and all. So as nanoparticle size increases, mechanical properties decreases. So how nano how nano the particle that will be used in the system, that mechanical property will improve. So size should be reduced has to increase the properties of the mechanical systems, right? Then addition, the amount, ratio, and nanoparticle size have a certain impact on the mechanical properties of nanocomposites. So, for example, the fracture toughness, flexible strength, and hardness of a ceramic composite can be better promoted by adding nano TIN, titanium nitrate, than by adding nano Al2O3 to the matrix. These are chemical compounds like upon adding to different chemical compounds. So the material brittleness or toughness changes. So according to requirement or according to application, that can be made either hard material or that can be flexible material. So by adding different chemical compounds. Okay, so and in this slide you can see that magnetic properties. So we have so far we have seen electrical properties, mechanical properties, and then now magnetic properties. So when it comes to magnetic nanoparticles that are ranging between 1 nanometer to 100 nanometer, generally display super paramagnetic properties. So it may increase by adding external magnet. So generally, if you observe that even in the sand also, when you keep a large magnet around it, small duct particles or like black spots will be attached to the big magnet. So that means the grain kind of magnetic material shows very, what do you say? Um, Effectively will come and attach to the big magnet. So their properties are super paramagnetic materials. So nanomaterials are more magnetic than bulk materials. That's what. So when it comes to bulk magnet, it may be hardly move to other particle to attract, whereas tiny particles are very easy to move and to revolve around any kind of other magnet. So easily they can be get varied from the required position from one point to other point. So nanomaterials are more magnetic than bulk materials. Even non-magnetic solid becomes magnetic when reduced to nanoscale. So even if it is non-magnetic material, but when it comes to cut it to the nano level, it shows or it exhibits little magnetic behavior. So as an example, sodium and potassium behaves like a paramagnetic at bulk, but a ferromagnetic at the nanoscale again. Ferrite, cobalt, nickel show a ferromagnetic behavior at bulk, whereas super paramagnetic at nano size. So this is one small graph is represented here. Magnetic properties nanoparticles. So magnetization, so this nanoparticle size, when it improves or when it I mean to say in the tiny mode when it is improves, that means as particle becomes very less and less, during that time the right hand side curve you can observe that it is raising, the magnetization part is raising. Okay, so when it comes to left hand side, x-axis left hand side, the magnetic nanoparticle size is little bit more. So their magnetization is done little, and finally it is becoming constant as as it reaches to some higher level of magnetization. Beyond that, it will not exhibit any other separate or different magnetization. So once it is get saturated with the amount of magnetization, how much it is absorbed, with that it will exhibit throughout the nanoparticle. So that is one characteristics we can observe under magnetic properties. Now let us see melting point, chemical under chemical properties, melting points. So nanoparticles has usually low melting points and reduced to lattice constant because they are of very tiny. So melting point is very compared to bulk scale materials. Their melting point is very um, uh, low, very low. So as well as lattice constant, they will come to constant at lattice due to change of surface energy to volume energy ratio. So decrease the size of the nanoparticles and the melting point decreases. So surface energy increases with the increasing surface area. And actually, this is in contrast, bulk material needs more energy or more power to melt, or for nano, it is not that much required. So, low melting point in the sense, the melting point is less required here. So, size of effect of nanoparticle melting point decreases. If you observe that this is a bigger circle at 200 amps diameter, and then this is 150 and this is 100. Then when it comes to dot, like at 50, between 0 to 50 diameter, it is showing like a dot. Now it is the temperature on the y-axis, for the bigger circle it is 1300 Kelvin, whereas when it comes to a small particle 500 Kelvin. So melting point is less, that means reduced inversely as the nanoparticle small size is coming. So melting point may be lower or higher for nanoparticles depending on the strength of the interaction between the particles and matrix. So it is not common to all kind of nanomaterials. That is the point where some kind of nanoparticles takes low melting point. And now coming to the next properties like uh, uh, this is reactivity and stability. So more reactive than bulk materials. Nanomaterials are more reactive, as we already discussed in magnetic properties and all. So they are as because of tiny size and more. fast active materials, also more reactive than bulk materials because of high surface area or surface energy. So when we break the bond to make nano size, so that means when the bulk size, if you observe that they are atomically bonded together, but when they become tiny, nanoparticles are tiny, so their energy each will get its equivalent energy. So the break of bond will give them more suitable to react with another kind of material, so it get high surface energy. The surface area reduces, size of the particle reduces, and then reactivity increases. In contrast, reactivity increases and surface area increases. So nanomaterials are extensively unstable. So generally, the tiny particles available, see, if you observe that they will be available on the surface of the material. So reactivity reduces and the stability increases. In contrast, reactivity increases, the stability decreases. So these are the important features or points we can observe under nano materials. And then coming to the next slides. These are like size of effect of nanomaterials. So just in the previous slide, we have seen surface effect, that is size of the particle available on the surface, on the surface of the material. So quantum confinement effect. This is generally we can call it as nanomaterial quantum confinement effect. So in the graph, you can observe that the bulk material with the higher group of elements, it is at 100 nano, and then 60 nano a little bit lower, and then 20 nano, 40 nano. So their disposition is very position. That means the movement or the confinement will be very, what do I say? Nanomaterials is different compared to bulk materials. Dispositions is very high. So coming to the particle size in the right hand side, energy, particle size is when the size of the particle is higher, their bond energy, that means mobility level to stable level. That means nothing but valence band to conduction band energy levels are low when the particle size is high. That's what particle size is high, they will be more stable as the internal energy gap is very less. But when it comes to coming to the particle size of nano, so they will be between level of energy band, that is valence band to conduction band, and they will be very active to move either into conduction band or either into valence band. Their energy, by supplying an additional of energy, a little bit of amount energy is sufficient for them to come out of its bond. So here, that is what in the previous slide we have seen, reactivity, how reactivity is less when the stability is more, or those two are contrast, right? So reactivity is less if the energy is high, or energy is less, reactivity is high. Like that, it is shown different materials like metal, bulk semiconductor, and then a semiconductor, single molecule, the reactivity and energy graph here. Then when it comes to uh, when the size of the material is reduced to nano scale, so typically that is less than 100 nano, its physical, chemical, optical, and electrical properties changes dramatically. So that's what till now we have seen those properties in the previous slides. So this is mainly happening because of the two phenomena. That is, one is surface effect. That is surface effect in the sense that the particle size is less. The surface to volume ratio increases. Because material is getting very tiny and tiny within the available volume, more nanoparticles will fit. So as more nanoparticles will fit, the reactions and their mobility, everything will be effect on the surface. So particle size decreases, surface to volume ratio increases. That means within the available volume, more number of particles will be incorporated, and a larger fraction of atoms lie on the surface compared to the interior. And these surface atoms are less stable. So so generally when you consider bulk material, within the bulk material we can observe that atoms, but when the atoms are tiny and the material are tiny, so the particles available on the surface itself, not on the inside of the particle, inside of the bulk. So as the particle it becomes its layer like a material, so all the atoms will be appear on the surface itself. So the surface atoms are less stable. So even with the small energy also they may come out of their local position and will go to reactive with other atoms. So more reactive and have unsatisfied bonds. So their bonds also about to their bonds also like very brittle to break easily. Then that is surface effect under nano size, and then as a resultant higher chemical reactivity, and the prone to lower melting point, and then enhanced catalytic activity, and the changes in mechanical strength and surface energy, and all these are the important parameters as a resulting under nanomaterials, nanoparticle level. So from the above slide, y-axis properties such as dispersion or reactivity increases sharply as particle size decreases. That we have noticed. So smaller particles show much higher surface effects. Then when it comes to properties, once again, deviation of properties with the size of the particles. So particle and then bulk level, nano level. If you see, copper at bulk level behaves like opaque, whereas copper at nano level behaves like transparent. So copper, if you make completely like a thin sheet, so we can observe one side of the particle, one side of the picture to the other side, that is transparent, it becomes like a transparent. Generally, copper has a sheet that will be used in medical applications or in preparation of semiconductor devices like that. A thin sheet will be used, this copper, for the conductivity where required. Similarly, platinum. So at bulk level, it behaves like an inert one, whereas at nano level, it behaves like a catalytic. How different, how to completely opposite behavior. And similarly, aluminum at bulk level it is stable, but at nano level it is a combustible. Similarly, gold, that material is also at bulk level solid, looks like a solid, but at nano level it looks like a liquid. So that everybody aware of gold, with pure this one behaves like a smooth kind of material. So similarly, that means hardness is very less. Similarly, silicon at bulk level it behaves like an insulator. At nano level it behaves like a conductor. So these are various properties, how they behave like at bulk nature, how they behave like nano nature. So now some more are features of nano structures. They will be generally based on these properties and based on these features, we can categorize nanomaterials. See, for example, the center one nanoparticulate materials. So if you take nanoparticles of type of ultra fine aerosols or nanocapsules type or quantum dot nanoparticles, nanotubes. So everyone is matter of nanometer distance. So 20 nanometer, 10 nanometer, like that. So less than 10 nanometer, like that. So based on those differences itself, you can find out various applications. For example, nanocapsules. So they you can find out applications like origin, natural and unintentionally released, manufactured. So these nanocapsules are also observed that under it is not that much difficult to get them to the level of nanocapsules easily can be identified. Similarly, when it comes to quantum dots, so chemical compositions are mainly required for identification of these quantum dots. So these quantum dots of kind of particles can be observed in metals or metal oxides, polymers, carbon, semiconductors, and biomolecules and compounds. Similarly, when it comes to nanotubes, so you can observe that aggregation state, single particles, segregates, and agglomerates. And similarly, ultra fine aerosols. These nanomaterials results in dispersion in gases, like observed in gases or liquids and solids, like gels, and ferrofluids and matrix materials. So in such applications, we can observe that ultrafine aerosols. Similarly, different shapes, spheres, needles, and platelets and tubes, all these can be observed with nanoparticles. And surface modifications, untreated as obtained in production process, coated, and surface modifications can be done, in which, as an example, nanotubes. So these are parameters. These are parameters are taken into consideration for characterization of nanomaterials. Based on these properties and characterization, applications are built with different shapes. So when it comes to applications of nanotechnology, this is very important. Where we can use nanotechnology, what are the applications? There are a lot of applications can be seen, like automotive industry, chemical industry, engineering, and then medicine, construction, electronic industry. So, for example, if you say automotive industry, so there you can observe that the construction of bulk materials converted into tiny and handy material, like lightweight construction, painting, fillers, base coat, clear coat, catalyst, and tires, sensors. All these comes under automotive industry. Then chemical industry, fillers for paint system, coating system based on nano composites. Then impregnation of paper, switchable adhesives, magnetic fluids, and engineering applications where we can see protection for tools, and then anti-blocking coatings, coating on plastic parts, lubricant-free bearings. These are all applications under engineering field. Then medicinal field, so drug delivery systems, active agents, contrast medium, medical rapid tests, and antimicrobial agents, agents in cancer therapy. So where not everywhere we can use this nanomaterials in construction, also construction materials, thermal insulation, flame retardants, then surface functionalized building materials for wood, floor, stone. So nowadays the construction of buildings are also changing with the changing in technologies. So nanotechnology going into that field also, facade coatings and groove motors, all these under construction side. Similarly, electronic industry, that is data memory, as how we are observing that memory card size is getting reduced and reduced as the technology increases. So OLED, FED, and laser diodes, glass fibers, optical switches, all these applications uses tiny particles of relevant nanomaterials. So that is where possible in every corner of the technology to build with nanomaterials. Then these are some more applications of nanotechnology: textile, energy, cosmetics, food and drinks, household and sports, outdoor. For example, food and drinks, packaging materials are of disposable kind of things, like environmental prone disposable material, which are made possible with the nanomaterials. Storage life sensors. For example, if the medicinal food, or the food which should not get spoiled easily, to put it in a better cover. So nanomaterial, it's made with nanomaterial of that kind of storage life increases. Then additives, then clarification of fruit juices, etc. All these made possible because of nanomaterial, various nanomaterial and their properties. And similarly, when it comes to applications of sensors, so earlier we have seen applications of various categories, but especially in engineering side, if you see the applications like sensors, and these sensors are not only engineering, the construction are of engineering side, but the applications are of medical side. So, biosensors, you would have heard about, or glucose sensor, or any kind of sensor. The sensors are generally made with nano kind of material inside, but the applications are related to electrical or medical. So, improved monitoring and detection capabilities. So, generally, we may use to identify blood cells, or to identify glucose levels, to identify cancer cells. So these are various kinds of scenarios where you can use nanomaterials inside to make the sensors, and accordingly they will use for different applications. So each sensor may have different capabilities for detection and then control. So environmental protection, risk management, more efficient use of materials, and more data and waste. Similarly, then coming to the treatment, like cleaning up of waste streams of contaminants, particularly those substances that are highly toxic. During that time, intervention of human will get reduced, but only based on the type of material that used for making of such applications. So nanomaterials are used. Those substances that are highly toxic will be easily dissolved into environment using that kind of type of nanomaterials. So that is cost effective, specific and rapid solutions for treatment of contaminants. And then another applications like cleanup of contaminated sites, problems brought about prior uh, technologies and past practices. Now, similarly, we can have applications like atom by atom construction, less materials to deposit of. One is two aspects, which are generation of waste products and streams, design and pollution prevention at the source. Similarly, applications of green energy nanoproducts such as solar and fuel cells could lead to commercially viable alternative clean energy sources. Nowadays, battery management, battery making also different comparatively previous bulk battery systems. Bulk battery systems may produce more pollution to the environment, whereas nowadays the sleeky battery designs are coming up. Due to that, environmental pollution also getting reduced. So, biodegradable batteries, like nano products such as coming up with less pollution, solar fuel cells are coming up. And not only these batteries, various systems which are used in like embedded systems, lightweight composites, and small compact embedded systems. Coming to the industrial applications like um, yeah, nano geochemistry, knowledge of formation of atmospheric aerosols, that movement of natural nanoparticles in air and soil can help inform the solutions to man-made problems. So here, this is another area where geochemistry, we can use nanomaterials for a better identification of solutions for the man-made problems. So similarly, implications of toxicity, so essential to risk analysis for ecosystem and human health. And similarly, implications of exposure, behaviorality, viability, bioaccumulation, implications of industrial ecology aspects, and all these are made possible because of the nano structure levels and applications of, because of vast applications of nanomaterials. So these are various advantages we can observe. um, So nanoscale processes for environmental improvement. That is one advantage with the nanoparticles, nanomaterials. And this is one more table application and example medicinal diagnostic drug delivery tissue engineering. So the application and example are putting together. If you see information and communication, this is one more that is memory storage, novel semiconductor devices, and then novel optoelectronic devices, displays, quantum computers. All this comes under category of information and communication. In the category of heavy industry, aerospace, construction vehicle manufacturers, and then in the category of consumer goods, foods, household, optics, textiles, cosmetic, and sports are examples. And environment, sensor-based control devices. So, for example, environment in the sense, if you see some airport, so the movement of door or anything, everything is based on the type of sensor and then smooth operation of the corresponding management system such that environment pollution avoided and then bulky kind of complicated material devices avoided. So these are all advantages of nano particles and nanomaterials with various applications. Then, in fact, applications are still continued, like carbon capture, sensors, and remediation, oil spill management, wastewater management, and energy drinking water purification. So all these will be having different levels of nano type structures, such that all these applications are can be made. Then it is one dimensional. Yeah. Coming to the synthesis, before synthesis of the materials, generally, what kind of structures can be seen in general? You see, nano-dimensional materials are of zero dimension, one dimension, two dimension. So, what is zero dimension? Generally zero dimension or is also generally people consider that zero dimension as one dimensional. Generally zero dimension means very tiny and which are very highly movable, like a gaseous particles kind of things. So people can be considered one-dimensional nanomaterials like layers, multi-layers, thin films, platelets, and surface coatings. They have been developed using particularly in the electronic industry. Similarly, two-dimensional nanomaterials. So coming to the one dimensional, it is like a complete flat surface, the very tiny and thin kind of thing of material. When it comes to 2D, that means it is having the x-axis and y-axis. Nothing but it is like a rectangle kind of thing, such dimension having two-dimensional. So the two-dimensional with which the applications are made are nanowires, nanofibers, varieties of elements like carbon nanotubes and subset of this group carbon nanotubes. Similarly, three-dimensional, that means the material is also having not only x-axis, y-axis, but also z-axis, like a cube. So these are applications where you can observe that colloids and quantum dots and nanocrystalline materials comes under this third dimensional nanomaterials. Now, coming to the structures for 2D, 0D, 1D, 2D. So, small particles are invisible. So, zero dimensional means which are very light particles and which are very highly mobile particles, very invisible. And small particles are very weight efficient and surface can be modified with the minimal material. So these are all advantages or benefits of small mm, particles. The behavior of nanomaterials may depend on more on surface area than particle composition itself. So because surface layer is more active compared to the bulk inside, so Nanomaterials, if you observe that all the nanomaterials, the particles are available on the surface. The behavior of nanomaterials may depend more on surface area. Now, coming to the next slide, relative to surface area. It is one of the principal factors that enhance its reactivity, strength, and electrical properties. Okay, so if you observe that large spherical particles do not cover much surface area. Previously, in one of the slides, we have seen large spherical particles do not cover much surface area, whereas nanoparticle equal mass of small platelet particles provide through coverage 1 to 10 to the power of 6 times more. So within the given surface area, number of particles, if they are very less, the coverage of nanoparticles is more compared to bulk. So by patterning matter on the nanoscale, that means when you make the particle very, very small and you can make them available as a pattern. So by patterning matter on the nanoscale, it is possible to vary fundamental properties of material without changing the chemical composition. That is one of the best advantage with the nano particles. So you can completely have the hold of the property of the surface area itself without going for chemical composition. So you can form the layer at your requirement, one portion of one type of nanomaterial, another type. So like that requirement based on that at nanoscale level, you can form the pattern of the material. So that is one example. And nano is a million times more efficient. In the figure, it is shown 25 nanometer as a thin surface layer compared to 10 micrometer like a circle particle. Now, particles in 1 to 100 nanometer range are opening up new vistas in surface chemistry for two reasons. Related to nanomaterials, so huge surface area with many of the atoms on the surface, thus allowing good atom economy in surface gas, surface liquid, and surface solid reactions. So generally, on surface only reaction will be more compared to the internal core. So here. Surface area, if it is more with nanoparticles, their reaction will be more. So here, if you observe that the graph particle size is increasing, the fraction of atoms at the surface is reducing. So if the particle size is reducing towards left hand side, if you go, so fraction of atoms at the surface is more. So the curve is that's why from top to bottom it is reducing as the particle size increasing. Now, enhanced reactivity due to crystal shape. So, for example, the shape changes from cubic to polyhedral when the surface concentration of edges and corner sides goes up considerably. So, the figure shows the smaller particle size, larger the ratio. So, another characteristics properties of nanoparticles is the quantum size and the band structure. Um, Now, you see specific surface energy and surface stress. So here, surface energy versus surface stress. So here, the concepts like material surface, they have different properties. Specific energy means reversible work to create unit area of a new surface at constant temperature. It is a scalar quantity. So it's actually surface energy is the energy where different from different surface materials. It is specific to that particular material, the energy on the surface measurable. The reversible work required to create a unit area of a new surface at constant temperature. So making the temperature constant volume. So within the available surface of unit surface, what is the energy that is work to be done? Work is done. Okay. So surface stress, that is the force per unit length. So definition of surface energy, generally how we take is work required to create unit area. Whereas in the case of surface stress, force per unit length, that must be applied to elastically deform a surface. So when the surface is having some material and having some energy. So when you deform, that means when the surface is like shape, curved shape, or when you bend like this, so that is stress. That means when the surface is facing some stress against to that work, so that is what surface stress. The force per unit length that must be applied to elastically deform a surface. It is a second order tensor that varies depend on the crystallographic direction. So in solids, unlike liquid, surface energy is not equal to surface stress. So surface stress is generally surface stress and surface energy, just like equal and opposite action and reaction. In that way, what is the amount of energy it is containing, that much of stress it feels when we apply force. But in the case of in solids, it is different. Surface energy is not equal to surface stress. That is one more point to capture. Then coming to effect on lattice parameter. So here surface energy and surface stress causes size dependent change in the lattice parameter of the nanomaterials, so which differ from their bulk counterparts. So the three effects of lattice parameters are lattice contraction, lattice expansion, and size dependency. So generally, based on the size, the surface stress or surface energy is changing. So generally, when you consider bulk materials compared to nanomaterials, these are different. When it comes to nanoparticles, the more available, they will be more available on the surface, and the surface energy is the one major role plays. So the lattice parameters are important to identify. So lattice parameters are of lattice contraction, lattice expansion, and size dependency. So what is lattice contraction? So in lattice contraction means coming closure, or contraction with some reaction. The particles or the surface may go into contract. So in many metallic nanoparticles such as gold or platinum, surface atoms are under coordinated compared to bulk atoms. So coordinated in the sense like they behave like a energy applied materials, like they will move in a same passion. Their random movement is less, whereas the movement will be same in all the atoms. So like that, surface atoms are under coordinated compared to bulk atoms. In the bulk atoms, what you observe is randomness is more, the overall resulting current becomes zero. But when it comes to thin surface materials, where you can identify all the atoms will be streamlined to move in a similar fashion. So this leads to shorter, stronger bonds at the surface. So, and creating a tensile surface stress. So, because of the bonding nature, you can observe that some stress already will be created on the surface. So, this tensile stress causes the overall crystal lattice to contract. So, because of that, that exhibits a shrink or a contract nature in the surface, with the effect of becoming more pronounced as the particle size decreases and the surface to volume ratio increases. So that is one effect because of the lattice contraction. The particle size decreases and surface to volume ratio increases. Now coming to the second one, that is lattice expansion. So what is lattice expansion? In some nano oxides, nanoparticles with absorbed molecules, the lattice can be expanded as particle size decreases. So as particle size decreases, why lattice will be expanded in the sense, as particle size decreases, more number of particles will be incorporated, so that in fact behaves like higher the lattice area. So this is caused by compressive surface stress. So when absorbent like surface surfactants bind to the surface, they increase the coordination of surface atoms. Like each atom will pull one atom between other atom. So because of the compressive surface stress, because of the absorbent behavior, so they will pull each other to one after the other, such that the lattice will be adjusted in such a way to incorporate more atoms. So causing a local bond, lengthening that can lead to overall lattice expansion. Similarly, the third one, that is size dependency. So the size dependency for nanoparticles, the size dependent lattice parameter change is most significant for particles smaller than 5 nanometer, with the effect diminishing for larger nanoparticles. So these are three parameters are considered to be considered under uh, lattice surface expansions. Now coming to the effect of phonon density of states. So the phonon density of states is also PDOS, describes the number of vibrational modes available at a given frequency. So surface effects in nanomaterials after the PDOS, which in turn influences the thermal properties like that, heat capacity and thermal conductivity. So this phonon density is like due to the behavior of due to the behavior of the particle, high energy at nano level. Because of this one, they will be more vibrant at high frequencies. So the frequency, as the frequency increases, the particles energy will go increase. So due to that, surface effects of nanomaterials alter the PDOs, that is surface density, phonon density. Generally, surface density is because of phonon density. Phonon is nothing but a small nanoparticle. So phonon density states describes the number of vibrational modes available at given frequency. So most of the nanomaterials are not same. As the nanomaterials are different, the PDOs will be different. Then phonon confinement in nanomaterials, a spatial confinement of a lattice vibration results in the quantization of phonon modes. So so if you make vibrations confined to the lattice itself, it results in quantization of phonon modes. This leads to a modification of PDOs compared to the bulk materials. That is phonon confinement. Now coming to the third one, surface induced stress relaxation. So these are all effects of phonon density states, will be considered under nanostructures of various applications. So the surface stress and corresponding lattice contraction or expansion directly impact the interatomic force constants. Okay, so this is little bit mixed with physics, nanophysics concepts. So restricted to your syllabus, you can concentrate on the topics which are relevant. In the case of lattice contraction, tensile surface stress, the interatomic force constant stiffen, leading to upward shift in the phonon frequencies. So higher energy phonons and a decrease in the overall PDOS. So this is another feature we can observe, that as the lattice contraction, that is tensile surface stress. In the previous slide, we have seen that. In the case of lattice contraction, and if the surface will be contracted, during that time interatomic force constants stiffen. So interatomic force constants becomes tightly bonding, because of tight bonding, leading to upward shift in the phonon frequencies. So phonon frequencies will be raised. So because of that, decrease in overall PDOS. Okay, so conversely, for lattice expansion, that is compressive surface stress. So the force constants soften and causing a downward shift in the phonon frequencies. It is vice versa. So if the contraction is reduced, that means that the surface tension, surface stress is reduced. Due to that one, force between or bonding between the molecules will be reduced. So because of that, there is a downward shift in phonon frequencies, obviously increase in PDOS. Okay. So if the phonon frequency is higher, PD voice reduces. If the phonon frequency reduces, so PD voice increases. Reverse. And effect of phonon density of states. So surface scattering, the presence of surface introduces boundary scattering for phonons, which becomes more significant in nanomaterials due to high surface to volume ratio. So actually, when you observe that the surface volume is more, so there is a shift of particles from one area to other area. That is causes that is because of high surface to volume ratio. The scattering mechanism modifies the phonon heat spectrum. So generally, the phonons, it is just like similar to charge gradient behavior that we see in bonding materials. So here it is scattering mechanism modifies the phonon heat spectrum. So when the phonons or the charger particles move from one point to other point, the phonon heat spectrum changes. So it changes thermal energy of the material also. So distributed among different phonon wavelengths. So this is another surface scattering feature that we can observe under nanomaterials. Then surface modes. Surface volumes, surface atoms vibrate differently than bulk atoms. So, which can lead to localized surface phonon modes not present in bulk materials. This can appear as additional features in the PDOS. Okay, then so here overall effects, if you observe that for nanomaterials, so features are like lattice parameter, then phonon density, then vibrational modes, phonon scattering. So if the question comes, so what sort of what sort of parameters that will get affect while decreasing the size of nanomaterial. So you can mention like the feature like lattice parameter feature. For that, what is the effect in the sense decrease or increase in the volume, that is surface to volume ratio. Then in resulting that, what will happen in the sense unbalanced forces are under coordinated surface atoms create stress like that. The cause, reason, and the feature, first of all, because of that, what is the effect it is causing, that you can write. And then what is the effect that is causing finally in the material, you can observe that. Then phonon density of states, for that modified frequency spectrum we can observe band gaps. Then as a result of that, quantization of phonons modes due to spatial confinement. Similarly, vibrational modes shift towards higher energy or lower energy. So vibrational modes. So interatomic bond modifications are leads to that, and then surface energy and stress finally. And then phonon scattering, significantly increased boundary scattering. The higher the surface to volume ratio increases the likelihood of phonons. So these are all features in which their effects can be observed. Then coming to the approach on synthetic nanomaterials, as mentioned in the very first slide, like bottom to top, top to bottom approaches, we can observe that there are two basic approaches for making the synthesis of nanomaterials. So generally, metal nanoparticles with a rather uniform size can be prepared by both physical and chemical methods. Okay, so here the physical method or the top-down method. So top-down or bottom-up. So top-down method is also named as physical method. Okay, so physical method in which metal nanoparticles are prepared by decomposition of bulk metal using mechanical force. So if you see, for example, how you sharpen the pencil such that the thick lead becomes like thin. In the similar way, decomposition of bulk material into small particles. So using physical method, using mechanical force or vaporization or laser absorption and so on. These are the various methods to make bulk material into small, which can provide higher energy to bulk metal than bond energy of the metal. So you need to provide more energy to cut the bulk material into small. So provide higher energy for the bulk material. So that is important here. And the in chemical method, for example, in chemical method, see when you, as an example, when you take sea water like salted water, and if you boil them for some time, you may get water. You may get salt out of the water, right? Some particles will come out of the water as water completely evaporated and resulting with a salt particle. So that is what it's a bottom up method. So a preparation of process starts from reduction of metal ions to metal atoms. So first of all, water you have taken that will be reduced into metal ions and that will be reduced into metal atoms followed by aggregation resulting in metal nanoparticles. It is bottom up. So both methods have their own advantages. However, chemical methods are considered to be better from the viewpoint of reproducibility, homogeneity, and mass production. So that is advantage with bottom up approach. So here, as an example, top down breaking down matter into more basic building blocks frequently used chemical or thermal methods. So top down nanoparticles, bottom up. Both will result in nanoparticles, but the process is different. Okay, then bottom up is building complex systems by combining simple atomic level components. Then bottom-up approach seeks to have smaller components built up into more complex assemblies, while top-down approaches seek create nanoscale devices by using larger, extremely controlled ones to direct their assembly. So the top-down approach often uses the traditional workshop or microfabrication methods where extremely controlled tools are used to cut, mill, and shape materials into the desired shape and order. Obviously, we require different techniques in order to get top-down approach. So bottom up or top down, which one is better? So micro patterning techniques such as photolithography and inkjet printing belong to this category. So bottom up approach in contrast use the chemical properties of single molecules to cause single molecule components um, to form self-organizing or self-assemble into some useful conformation or rely on a position assembly. So according to requirement or according to the necessity, people will use either bottom-up approach or top-down approach. So here clearly you can see that top-down approach, a bulk material can be taken into pieces till you get the nano level. Whereas bottom-up, in the sense, procuring the tiny portions and bringing them together finally to get into final product. That is what a bottom-up approach. And the microscopic material, this is what where bottom-up approach, microscopic material through which large structures are two small structures top-down, that is resulting in nanostructures. Similarly, molecules from molecules, small structures grow to larger particles, that is the bottom-up. This is one more representation. So bottom-up approach refers to the construction of nanomaterial from bottom, atom by atom, molecule by molecule, or cluster by cluster, whereas bottom-up approach are used as the building blocks to produce nanoparticles, nanotubes, nanorods, thin films, or layered structures. And this is one more representation, atoms and molecules together, chemical or physical process to bring particles or nanotubes and layers. Okay, so in the bottom-up approach, they chemically assemble themselves by recognizing the molecules of their own type. This approach starts by a collection of combining atoms and molecules to build complex structures. Um, so here, bottom-up approach, some more examples. So synthesis of large polymer molecule is a typical example. Large polymer molecule synthesis for bottom-up approach, in which individual building blocks like monomers are assembled to large molecules are polymerized into bulk material. Fabrication of integrated circuits like different components, resistors, capacitors, transistors on a PCB is one more example. Bottom up. That is, see, taking a PCB, incorporating resistor, capacitor, and all finally to build a system. It is bottom up. Similarly, crystal growth, where growth species, either atoms or ions or molecules, are utterly assemble into desired crystal structure and growth structure. This is another example. Colloidal dispersion in the synthesis of nanoparticle, nanolithography and nanomanipulation, production of salt and nitrate in chemical industry, the growth of single crystal and deposition of films in electronic industry. All these come under bottom-up approach. Now, so those approaches provide tremendous freedom among the resultant products. The number of possible um, structures to be obtained in comparatively small. In order to obtain the ordered structure, bottom-up process must be supplemented by the self-organization of individual particles in which the atoms or molecules arrange themselves into a structure due to their natural properties. Crystals grown for the semiconductor industry provide an example of self-assembly, as does chemical synthesis, large molecules. Um, so, few more slides with the different examples, like physical and chemical processing methods, physical technique, physical vapor deposition, in which involvement of condensation of vapor phase phases. So, evaporation, sputtering, plasma, laser ablation, all these processes under physical technique, whereas CVD, chemical vapor deposition. So this is self-assembled monolayer electrolytic deposition, salt gel method, and microemulsion pyrolysis. All these are bottom-up approach techniques, and this can happen either in gaseous stage or liquid stage, according to requirement. So coming to the top-down approach, as bulk material will be cut down into smaller required level. So I'm just skipping some of the slides because slides are repeated. Yeah, in top-down approach, a large-scale object is progressively reduced to dimensions. It consists of ultra-fine micro machining of materials using lithography, epitaxy, and etching. So, if you see the picture, bulk is cut down into fragments, that is again cut down into nanoscale particles. So, for that, we require a fine lithographic process. Similarly, epitaxy, etching, it's like IC making from the wafer. Okay, so creating circuits on the surface of a silicon microchip by etching. So this is an example. And attrition or milling in making nanoparticles, then lithography may be considered as a hybrid approach. So this is one more: physical processing methods, mechanical methods, lithographic techniques. These all comes under top-down approach. Starting material is solid state, whereas in the bottom up, that could be gaseous or liquid. So some of the advantages, disadvantages are shown top down, up, and bottom up. Advantages are large scale production, deposition over large substrate, that is advantage on the top down. In the bottom up, advantages are ultra fine nanoparticles, nano shells, nanotubes can be prepared. And then in the top-down approach, one more exam advantage, chemical purification is not required. In the case of this one, narrow size distribution is possible up to 1 to 20 nanometer, cheaper technique. Then disadvantages under top-down are broad size distribution, 100 to 1000 nanometer, varied particle shapes or geometry. So control over deposition parameters is difficult to achieve. Whereas the bottom-up approach, disadvantages, large-scale production is difficult. So chemical purification of nanoparticles is required. So these are some of the disadvantages. And a more expensive technique is top-down approach because we need to have that fine cutting tools we require. for making the nanoparticles. Coming to the precipitate method, yeah, synthesis of nanoparticles based on the precipitate method. So, what is precipitation? Generally, you might have studied in your school life precipitation in the sense deposited substance in a solid form from a solution. So everybody aware of this. Precipitate means preparing a solution from the solid. So what is a precipitation process? This method relies on precipitation of nanometer-sized particles within a continuous fluid solvent. Okay, so as an example, widely used for metal oxide to build, or metal halides to build, or two hydroxides to build. So generally precipitation method is a chemical synthesis. So what is precipitation? It is a chemical synthesis technique where an insoluble solid that is precipitate forms from the reaction of two soluble precursors in solution. So if you dip two insoluble that means two soluble precursors, if you use in a particular, you dip in a solution, you will be getting a resulting solution. Resulting one is a precipitation. Okay, so as a result, you'll be getting a precipitation. So, for example, metal oxide, so zinc oxide and titanium oxide are formation of titanium and oxide. Similarly, zinc and oxide. Similarly, metal halides. So that is silver bromide and silver chloride. So Ag and chloride, if you add together, it will be resulting from silver chloride. Okay, similarly, hydroxides. Ferrite and OH3. Now, so the synthesis by precipitation requires four steps, which are nucleation, precipitation, filtration, calcination. So, what is nucleation? Nucleation means an inorganic metal salts such as chlorides, nitrates, etc., are dissolved in suitable solvents. So, that is nucleation. Precipitation means metallic salts are precipitated out of hydroxide or oxide or halides using NaOH or NH4OH or potassium bromide in a suitable solvent under constant and continuous stirring. So filtration means the participated product is filtered and washed to remove impurities. Okay, then calcination, filtered product is dried at high temperature under pressure to obtain metal oxide or metal halide or hydroxide nanoparticle. So these processes actually, nucleation means inorganic metal salts such as chloride are dissolved in suitable solvents. Inorganic materials to be dissolved in suitable solvents, that is nucleation. Precipitation means joining or adding to materials to get hydroxides or oxides or halides. And third technique, filtration means precipitated product is filtered and washed to remove impurities. And calcination means at high temperature or under high pressure, obtain metal oxide, metal halide, or hydroxide. And this fourth one and second one are similar, but fourth one needs more high temperature compared to the precipitation method. So at high temperature under pressure to obtain metal oxide, metal halide, hydroxide nanoparticles. So synthesis of nanomaterials by precipitation method, the size of nanomaterial can be controlled by varying stirring speed, time, temperature, and drying. So if the saturation occurs for longer time, that means while making the precipitation, the saturation period occurs for longer period, then the precipitation results in larger size nanomaterials. That means if the saturation, that means for example, if you keep for longer time the saturation level, you'll be getting more bulky material. Other than if you wanted to get nano kind of material, the saturation level or period should be less. So that's why people, while making nanomaterial using precipitation method, the time is important. So stirring speed, time, and temperature of drying. Then These are examples of nanoparticles making. So this is actually double jet precipitation apparatus. So through this double jet, two compounds of materials will be put it into single cabin, that is mixing device with heater. So silver nitrate and silver bromide solutions are introduced into the mixing device. That mixing device is known as double jet precipitation apparatus. The mixing device is attached to the end of high speed motor with control speed of about 2000 rpm. Then temperature is maintained at 70 degrees centigrade. Stirring the mixture at regulated speed, and silver bromide nanoparticles of size 7 to 60 nanometer are obtained. So while continuous stirring of the material, the particles will get separated. So that's what high speed motor results in nanoparticles in this whole setup. So this is one more overall reaction. If you write in terms of chemical compounds, so silver nitrate plus sodium bromide results in silver bromide with NaNO3. So here, silver bromide is the required nanoparticle. So synthesis of silver bromide nanoparticle is one example here shown. So for this silver nitrate, sodium bromide are used as the compounds. Then this is one more copper oxide nanoparticles formation. So for that, we require certain amount of copper sulfate pentahydrate, then mixed with the 25 grams of hydroxyl ammonium chromide, ammonium chloride, and the mixture is cooled in cooled water, and then constant swirling is required. A solution containing 40 grams of sodium hydroxide NaOH in 750 ml of distilled water is added to the mixture. So the precipitation is settled down and supernatant liquid is poured off. Generally, see for example, if you keep some rice flour in water, it will not completely dissolve in water, but some amount of rice flour will go down, and a thick kind of material will be seen in the water down portion. So that's what precipitation. Okay. So settle down at the down liquid. So the amount of water which is on top will be removed, and the remaining part, if you observe that is what precipitation. Okay, the precipitation washed several times with the distilled water until it chloride free. The precipitation is dried at 200 to 250 centigrades. When the precipitation is heated to 300 degrees centigrade, then copper oxide is formed. So this copper oxide, if you observe that like a black portion on the right hand side, but that the equipment is shown in order to get this copper oxide. So this is a pure copper oxide nanoparticle. This has got many applications. This copper oxide. So like that, every nanoparticle have its own processor having necessary compounds to combine, and using precipitation method or using top-down approach or bottom-up approach according to requirement, nanomaterials will be made. Then this is another um, copper oxide representation, and this is chemical reaction. So finally, copper oxide with copper will be generated. The advantages, if you see, simple and widely used for production of single and multi-components, oxide nanopowders, easy control of particle size, good control on composition of nanoparticles, various possibilities to modify the particle size, surface and homogeneity. Then coming to the hydrothermal and mm, solvothermal methods. So hydrothermal solvothermal process is defined as performing chemical reactions in solvents. So performing chemical reactions in solvents contained in sealed vessels, in which The temperature of solvents can be brought to around a critical points via heating concurrently with autogenous pressures. So there are key points like it is the process is happening in chemical reactions which are solvents. The solvents are to be sealed in a vessel, sealed vessels to be kept in sealed vessels, and the temperature should be maintained to the critical point while making the solvents. Okay, heating concurrently with autogenous pressures. So involves heating the reactant in a closed vessel. That is important. Closed vessel with water at high temperature and pressure. The hydrothermal when water is used as a solvent, and salvothermal when organics are used as solvents. So here two things: thermal and salvothermal methods. So thermal means which uses purely water, that is hydrothermal. Salvothermal means when organics are used as a solvents. Solvents means, for example, when you mix sugar in water, the water becomes a solvent in which sugar is mixing. So, solvent is the one which is taking another material, absorbing. So, that is what solvent. Okay, so here, autoclave is heated, pressure increase and water remains liquid above its normal boiling temperature, superheated water, and this condition is known as hydrothermal condition. So what is hydrothermal condition? So at high temperature, the level of pressure increased and water remains liquid. So pressure increases but water remains liquid above its normal boiling temperature. That is superheated water, which is called hydrothermal condition. And the following terms are commonly used when describing solvothermal or hydrothermal process. One is the precursors, then second one is the mineralizers, and then additives. So precursors are like reactants in form of solutions, gels, and suspensions. So before getting the hydrothermal or solvothermal, the solvents should be identified first of all. The solvents are nothing but reactant solutions, which are also called as precursors. So mineralizers, which are when the temperature is sufficient, when the temperature and pressure are insufficient. When the pressure and temperature are insufficient, um, to dissolve the starting material, alkali or metal salts as mineralizers can be added. So, during the process, for example, when the temperature and pressure are insufficient to dissolve the starting material, so the process when it is started with what are the solvents. So, during that time, we can add salts or mineralizers can be added, alkali or metal salts added in high concentrations, which are of 10 m, and also helps to control the pH of solutions. So that's what mineralizers. Then additives. So these additives are like organics or inorganic, relatively low concentration, added to promote the particle dispersions or to control crystallic morphology. Now coming to um, the first, generally when it is started in 1960 actually, with an experiment by two people, the technique to characterize nanoscale products, where that time it's not available, that's insufficient to successfully realize the control of crystal growth, and the process has gained great success in manufacturing nanomaterials with the crystallinity and morphology and size control. And the reactions proceed in a sealed reactor autoclave. Teflon or alloy linings are containing an extra can beaker or tube made of Teflon. So if you see this picture, it's a Teflon cup in which water is added, and downside to the water, you can see solid reagents, and then everything is kept under stainless steel shell, and it is covered with stainless steel lid, and bursting disc. So this is Teflon or alloy linings are containing an extra can beaker, so to protect the autoclave body from the highly corrosive solvent which is held at high temperature and pressure. Okay, so in some cases, a Borden gauge is fixed to the autoclaves to directly monitor the pressure and stirring accessories of to minimize the concentration gradient inside them. So while preparing the nanomaterials, this is another method. Okay, so some temperature and pressure measurings are given here. Quartz tube, for example. In order to get the quartz tube, the temperature required is 250 degrees centigrade under the pressure of 6. Similarly, cone closure 750 to 1150 and pressure is 4000 to 13,000. Welded closure and then modified Bridgman autoclave and piston cylinder, opposite diamond anvil. So these are various reactors for hydrothermal solvothermal processes with their initially designed operating temperatures. So temperature, pressure, and corrosive resistance of reactors materials are most important parameters. So the important parameters are temperature, pressure, and corrosion resistance for the reactive materials. And the work conditions might vary depends on the materials and reaction solutions. Um, So solvents to be used, which are like water or ethylodyamine or methanol or ethanol or toluene. So critical temperatures, and each solvent have its own conditional parameter like critical temperature and critical pressure. Um, that is for water, for example, temperature is 374, whereas the critical pressure is 22.1. So based on the property of solvent, the material will be used for further decomposition or growth. So resulting reduces solubility of solute species, leading to high supersaturation in the solution. Mm, So one more is solvothermal process, an alternative to the hydrothermal process. So here, nano aqueous organics are supercritical solvents or solvents mixtures are used, analogous to the hydrothermal process. So, example, methanol, ethanol, toluene, or butane is the one which will be used like the gas present in the cylinders. Okay, so solvothermal process can make the reactions occur at relatively low temperatures and pressures. The solvothermal processes can handle precursors that are sensitive to water. The products derived from the solvothermal process are free from foreign anions, and morphology or crystal phase control can be easily realized. And a lithium battery cathode material can be synthesized phase pure at 300 degrees centigrade and 38 MPa in 5 minutes in supercritical water ethanol mixtures. So, like the salvothermal process is a um, little bit better compared to hydrothermal processes. And this compound is particularly difficult to prepare by conventional solid state routes because high reaction temperatures are required and very easily oxidized and is a large some materials are not expected to occupy tetrahedral sites easily in the lithium crystal structure. So, based on the type of material that you use for the process, it will be little bit difficult compared to a hydrothermal process. Servothermal process can handle precursors sensitive to water. That is point. Coming to advantages under servothermal, low process temperature compared to hydrothermal, performance of reactions in liquid environments, low energy consumption, environmental benignity advantage, and hydrothermal synthesis can generate nanomaterials which are not stable at elevated temperatures. So, like the some advantages can be seen, suitable for growth of large, good quality crystals, simplified and precise control of the size, um, mm, and the materials which have higher vapor pressure near their melting points can be grown by the hydrothermal methods. So, hydrothermal synthesis can generate nanomaterials which are not stable at elevated temperatures. So, some of the advantages can be seen in the servothermal processes. Now, mm, disadvantages, coming to the salvo thermal disadvantages, need expansive autoclaves, safety issue during the reaction process, impossibility of observing the reaction processes. So some reactions may be unknown, so can be lead to black box kind of reactions. So suitability of such methods for scaling potential uses. So almost we are coming to the end of the PPT. So these are all actually for preparation of nanomaterials. What sort of what sort of method can be used? What sort of type of application, based on the application? What sort of method will be used? So for zeolite synthesis, for example, for zeolite synthesis, the final stage is to heat aluminosilicate gels hydrothermally to crystallize the zeolites. So this is the chemical reaction generally used for geolite synthesis. Many phases can be prepared by hydrothermally at much lower temperatures than would be required for solid state reaction. So to produce a magnetoplumbite phase, hydrothermally can be carried out at much lower temperatures. So here, based on the requirement of whether it is which type of nanomaterial to be used, where we can use the hydrothermal process or servothermal process, that depends on the type of nanomaterial you require finally. Um, and most of the nanomaterials require chemical kind of preparation. So single crystal or quartz SiO2 which are used piezoelectrics in a range of applications are grown hydrothermally in a temperature gradient using arrangement. Arrangement is like this hydrothermal crystal growth process. So enriched solution of the silicon oxide is melted in solution. You might have studied in VLSI like crystal growth ingot, uh, Jokrowski process, no? So in the similar way, there is one chamber. In this chamber, silicon oxide will be used in melted position. So this mixture will be used at some temperature, and a seed crystal on which the new growth forms. So the seed crystal will be dipped into uh, that the silicon dioxide melted portion. So in that case, when it is happened, when it is done in that, the ingot, that means that seed crystal will be coated with the melted silicon dioxide, and on the seed crystal, the coating of SiO2 will be formed. So that will be taken out. So SiO2 will be formed on the seed crystal. SiO2 is only sparingly soluble in water. When NaOH is dissolved in water, solubility of SiO2 increases. So the solubility of SiO2 and NaOH solution increases with increasing temperature. So this is basically the process to improve the quartz crystal by hydrothermal treatment. Now coming to the preparation of synthesis uh, gemstone, synthetic gemstone industry. So generally, the gems, that means the people who wear in their rings or any other ornaments. No. So the gemstone industry, the process requires heat and pressure and imitates the conditions deep in the earth that results in the formation of the natural gems. So gems, how that will be generally produced accordingly, that kind of environment will be prepared to create artificial gems. So nutrients are dissolved in water solution and then synthetic crystals form a solution cools. So one more that is process, bare process for the extraction of one A1203 forms bauxite. So this is commercial extraction of aluminum oxide prior to production of aluminum metal. Bauxite is dissolved hydrothermally in sodium oxide solution, from which gibbsite and Al2O3 3H2O is precipitated and heated to produce anhydrous alpha Al2O3. So this is some levels of chemical compound should happen here. Bauxite will be converted into aluminum oxide. So preparation of numerous nanostructured metal oxides such as aluminum oxide, copper oxide, ferro oxide, and similarly other through both hydrothermal and solvothermal processes. So here in the table, the representative binary metal oxide obtained through hydrothermal or solvothermal processes. Okay. So what is the starting material? What is the solvent used? Particle size, how much, and morphology. Morphology in the sense the making outer shape. So compared to hydrothermal process, solvothermal process could produce metal oxides that are smaller and have a narrower size distribution. That is one of the important key point to be remembered. Hmm. So titanium oxide, just I'm skipping. You people can self-study on this. So this actually in the first year, in this end of the unit one actually, and so unit one totally consisting of types of nanomaterials, types of mm, based on the scale of nano length, what type of applications can be seen at nano material level, and what are the applications, various fields, their properties, electrical property, mechanical property, and biological property, all this we have seen. And then we have seen approaches, synthesis approaches like bottom up and top and bottom approach. Then we have seen precipitate method for the synthesis of nanomaterial, then chemical salvothermal, hydrothermal methods. So this is all comprises unit 1 and 2 together. Whereas in another PPT, we'll be discussing about carbon nanotubes, um, carbon nanotubes as additional topic. So with this, I'm winding off.